Okay, hello everyone. Welcome to the lecture, and please confirm that you can hear me clearly and see my slides. Thank you. Thank you. Okay. So what we were doing last lecture. In the last lecture, basically we talked about what is the proper uses of general purpose registers, right? Or if there are some points which need to follow or uh, rules which we need to follow while we are using the general purpose register. One thing. Second, we briefly talked about the main concept of pipelining, right, in a very simple way. And third, we also talked about the features of a risk processor. So today we are going to focus at branch instructions, right? Branching, and I don't think we will be able to cover more arithmetic instructions, but we will be focusing more on branching. Okay, so before we talk about branch instructions, we first need to again revisit status register. If you remember, we said that status register has 8 bits, and actually all of those 8 bits are known as flags. So we covered zero flag, carry flag, and half carry flag, right? Now, the important thing is that zero flag and carry flags, they are used when we are comparing unsigned numbers. Uh, However, they are not sufficient for comparing the signed numbers, right? So that's why we have some more flags, negative flag, and V, our flag, overflow flag, and S, sign flag, which is all three of them and are combined with Z flag, and then they are used when we want to compare the signed numbers, right? How? We will talk about them, like how these N, V, S, and Z flags are used for comparing signed numbers. We will talk about this in our future lecture. Today, we will focus only on how Z and C flag are used in comparing unsigned numbers with each other. And why we are even talking about comparing unsigned numbers, because we are going to talk about the branch instructions, and branch instructions basically look at the value of these flags. Okay, so and these value of these flags are set by as a result of comparison. Okay, so mm, let me first give you a quick overview of like how zero and C flag they are used when comparing unsigned numbers, and then I will go to the next slide. Let me connect my drawing pad, and then we will go to OneNote, and I will explain. Okay, so where is OneNote? Here. Let me open a new page, not new page. Don't sync, not now. I don't want you to sync. Please go away. Okay, not new file. I need to open new section, right? So week 4, day 2, and the page is page 1. Why can't I write it? What's going wrong? Something is wrong. Oh, okay. It wants me to sign in, I guess. Okay. Yeah, I think I need to take care of this. So, okay, I think I can take care of that later. Signing in. I don't want to waste time now. So, okay. So what we were talking about, we were talking about how Z flag and C flag, they are used in comparing two numbers, right? So to comparing two unsigned numbers. Let's say I have two number A and B, right? And I want to compare them. If I want to compare them, there are three possibilities. One, what is A is less than B? Other is A is greater than B, and the third is A is equal to B, right? So these are three possibilities, and I'm talking about unsigned numbers, right? So let's say I take 4-bit value of A. Let's say it is 5, and B is equal to uh, 4, right? Now I'm writing 4-bit values of both signed unsigned numbers. So this is 0101, and this one is 0100, right? Now let me, so what I can do is that for comparison purpose, I can say, okay, let me perform A minus B, right? So when I do A minus B, what will I get? 1, 0, 0, 0. And if this is my most significant bit, let's say, since I'm saying a 4-bit number, so there is no borrow in, right? So there is no borrow in. So what will be the value of my C flag and value of my Z flag? Anyone who want to answer can unmute and respond. Please go ahead, unmute yourself and you can talk. What will be the value of C flag? Okay, C is equal to 0, Z is equal to 0. That's true, right? So C is equal to 0, Z is equal to 0, right? This is the case when A is greater than B, right? Now let me use a number value where A is less than B. So let's say A is equal to 4 and B is equal to 5, right? So again, I am simply writing the binary values, and I I want to do the subtraction, A minus B. So I cannot subtract 1 from 0. So I take a borrow here. So if when I borrow, here I will be left with 0, and I will borrow 2, and then I will borrow 2 to the next position. So here I will have 2, and in this position I will be left with 1. So 2 minus 1 is 1. 1 minus 0 is 1. Remember, here I was left with only 0. Now I need to take borrow into most significant position. So 2, but then when I move the borrow to the next position, here I will be left with 1, and here I will have 2. So 2 minus 1, 1, and 1 minus 0, 1, right? So in this case, what is value of C flag and what is value of Z flag? Yeah, so the C flag will be 1. Why? Because I have borrow into most significant bit position, and Z flag is 0, right? The value is non-zero, right? So this is what I get when A is less than B, right? Now let's consider the third case, right? And here I'm saying A is equal to 4, B is equal to 4. So 0, 1, 0, 0, 0, 1, 0, 0. When I do the subtraction, 0, 0, 0, 0. What is the value of C flag and what is the value of Z flag? Yeah. So sorry. So the C flag, will be 0, but the Z flag will be 1, right? So this is the case when A is equal to B, right? Now, so if I have two numbers A and B, and if I subtract them, and after subtracting, if I look at the value of these flags, what information can I get? If C is equal to 0, And see if C is equal to 0, so it's mean A is greater than B, right? If and provided that Z is also equal to 0, right? And if C is equal to 1, it's mean A is less than B. But if C is equal to 0 and Z is equal to 1, then it's mean A is equal to B, right? So everyone with me on this? So if first thing is you can directly look at C, C is equal to 1. If it is equal to 1, A is less than B. If C is equal to 0, then there are two cases. Look at the value of Z. If value of Z is equal to 0, then it's mean A is greater than B. If value of Z is equal to 1, it's mean A is equal to B. Okay. Is it clear to everyone? Okay. Okay, good. So then I can get back to slides. So this is how we can use the Z flag and Z flag and carry flag for purpose of comparing unsigned numbers. I am not going into the detail of the second part of this slide, the lower bottom part of the slide, but just I want to highlight that if you want to compare the signed numbers, then just looking at the value of zero flag and carry flag is not sufficient. For that, we also need to look at the value of overflow flag, negative flag, and signed flag, right? Why? I will explain it like in the lecture. We will talk about comparing signed numbers, but for now we are focusing at comparing unsigned numbers, right? Okay. So branch equal instruction. This is an instruction which actually uh, looks uh, which basically looks at the value of Z and C, and the assumption is that Z and C flag, their values are set uh, after subtracting uh, after comparing unsigned numbers. So which basically mean that if you want to do a branch based on comparisons of signed number, you should not use the branch equal instruction. If you want to do branch based on the comparisons of unsigned number, then you should use the branch equal instruction. Okay. So this is the syntax branch equal K. So where K is what? K is the destination address of the instruction where you want to jump. When we'll see a complete example, then it will become more clear to you. So here is like the code or the format of this instruction. So most significant 6 bits are 4 ones and zeros. Least significant 3 bits are 0, 0, and 1. And in between, you have the 7-bit value of uh, K, right? So instruction itself is 16-bit, okay, not 8-bit. The instruction code is 16-bit. So if you have 7 bits, K is basically like K is the address of the instruction where you want to branch. Branch mean where you want to go, right? So if you can use only 7-bit to specify the address of the instruction where you want to go to the target instruction, and if K is a 2's complement number, then it means, if you remember from one of our previous lectures, then what will be the range of the value of key K if K is a 2's complement number? Its value range will be -64 to +63, which means that if in your program where you have this branch instruction, I'm just writing branch for that branch equal instruction. So, and you are saying here you are specifying K. So K can be anything uh, in the range of 63 instructions in the forward direction and 64 instructions in the backward direction. Okay. So it cannot reach instructions too far. So like if you want to jump to an instruction which is, let's say, in the forward direction, but let's say at position 100, relative position 100, relative to the location of branch itself. So you cannot use this branch instruction because the maximum is 63 forward. Similarly, if you want to go backward, let's say -100, you can't use this instruction because it cannot go too far. Okay. And that is basically coming from the restriction is coming from the fact that the destination is specified only using 7-bit code, And if you have 7-bit code and it is a 2's complement number, then the maximum range is minus 64 to 63. So after the execution of this branch instruction, your hardware updates the value of the program counter, right? So if so here basically we are saying branch equal, right? Now, just like a few minutes ago, I showed you on note on what this on one note. So if two instructions are numbers are equal, unsigned numbers are equal, what is the value of Z flag? The value of Z flag is 1, right? So what does this instruction do? It actually looks at the value of the Z flag. If Z flag is 1, it's mean those two numbers were equal, and that's why it will take the branch. It will go to the destination address. Okay. And for going to the destination address, what happens that program counter is the value of the program counter register is updated. How? It is updated by adding PC plus 1 plus K, right? What is the PC? PC is the memory address where branch equal instruction itself is located. And how new PC is calculated? By adding to it 1 plus K. Okay. So when we'll see example, it will become clear to you. But as I said, this instruction checks the Z flag. In case that the Z flag is not equal to 1, which means that those two numbers are not equal, then K is not added. PC is how updated. PC is updated only by adding 1 to it or by incrementing it by 1. Okay. Is everyone clear on this? Okay, thank you. So, if you still have confusion about how this PC plus 1 plus K is calculated, we will see a couple of examples and then it will become clear to you. Okay. So here we have seen only one instruction, branch equal instruction, right? So it is we name it as conditional branch, a conditional jump. Why we are saying conditional? Because it checks the value of Z. If the value of Z is equal to 1, then the branch is taken or then the jump is performed. But if the value of Z is not equal to 1, then branch is not taken. So that's why we name it as a conditional branch. But this is not the only example of conditional branch instructions. There are many other branch instructions, conditional jump instructions, or conditional branch instructions in your AVR microcontroller. All of them are listed here. I'm not going to read their names, right? However, if like let me like explain a couple of them. Like for example, this one, branch CC and then label. Label is basically nothing. It is the label in your assembly language which is pointing to an instruction in your program, right? And branch if carry cleared. So what does the instruction do? It will look at the value of the carry flag. If the carry flag is 0, then it will jump to the location which is pointed by this label, right? And actually all of these instructions, they check one of these flags. Okay. There are some other instructions, for example, this instruction, branch if T flag is set. And how you set the T flag? By calling the SCT instruction to set the T flag. Similarly, how you can clear the flags by calling CLT, and how to set the interrupt flag SCI, how to clear the I flag CLI. Actually, we will talk about these instructions in more detail in later lectures on interrupt handling. But for now, we will not be using them. I just wanted to like explain here that how these flags can be set. Just like for example, we know how carry flag is set, how Z flag is set, or how H flag is set, and later on we will see how S, V, and N's value of these flags are set. Similarly, there are some situations where value of I and T flags are set, right? So specifically, the value of I is set when we enable the interrupts, and this T flag you can manually clear or set it by putting an instruction in your program. Okay. So these branch instructions, this one, which we have seen in the table, you actually use each of those branch instruction, are not each, most of those branch instruction in comparison, in combination with the with other instructions. And that other instruction which we mostly combine with the branch instruction, one of those instruction is compare instruction, right? CP. So what is the syntax of CP? It is like, you write the name, not name, acronym CP, and then destination register and the source register. And what does this instruction do? It calculates the result of RD minus RR, but it doesn't write the result back into RD. It doesn't write the result back in RD. Clear, keep it in mind. It only calculates the result, and based on the results, it sets a flag. It doesn't write the result of subtraction back into the destination register. So it is not subtraction instruction. Because in subtraction instruction, what happens that the result of subtraction is written back into the destination register. Here we are not doing that. It will just set the flags in status register based on the result of the subtraction. Okay, so I said that this compare instruction is used in combination, is like used in combination with branch instruction. So let's say you first put in your assembly program, you first put the compare instruction, and then after that you place a branch instruction, branch equal instruction, right? So here what you are saying, branch if equal. What does then it mean if your program has like these two instructions in sequence? So it is basically you are saying that you are first setting the flag. This instruction will set the flags based on the subtraction, right? And then this instruction, the second instruction, it will look at the value of the Z flag. Who has set the flag? This instruction, previous one, right? So if the value of Z is equal to 1, it's mean that the content of RD and RR register was same, right? So if the content was same, so it's mean that both operands were equal. So now you can, the jump will be taken to the label specified as part, as part of the instruction, right? So PC will be set equal to PC plus K plus 1. Okay. And branch not equal, we also have an instruction branch not equal, which actually, so again, for example, now let's say you have a program in which you first wrote this compare instruction, and the next instruction is this one, branch not equal, right? So again, same thing will happen. Source register will be subtracted from destination register, and based on the result, the flags will be set. And then your branch not equal instruction, it will check the value of again Z flag, but this time the jump will be taken if the two operands were not equal. So one not equal mean that jump will be taken if Z flag is equal to 0, right? Is everyone with me until this point? If any confusion, please let me know. Okay. We have another instruction, branch same or higher, right? So branch same and higher, it actually, again, you will do the same thing. First, you will put compare instruction in the program, and then after that, branch same and higher. So branch same and higher, it will basically, what it will do, if the value of the destination register is same or greater than the value or higher than the value of the source register, right? So when how we can detect it by, how we can know it by looking at the value of the flags, by looking at the value of C flag. If the C flag is equal to 0, it's mean that destination is either greater or is either higher or same as the content of the source register, right? And branch low, this is the case when, remember what I showed you on the, when I showed you on the, on OneNote. So this is the case when A is less than B. If A is less than B, then what? C is equal to 1, right? So we are saying like branch if lower, if A is lower than B. So basically you are saying if RD is lower than RR, right? So if that is the case, then jump to the target. Okay, so these branch, if say a branch same or higher and branch lower, these are actually used when you are comparing the unsigned numbers. What does it mean? It means that the numbers which you place in RD and RR, they are treated as unsigned numbers, right? They are interpreted as unsigned numbers, right? And when you use BRSH and BRLO, branch same or higher, branch low, you are actually telling the microcontroller that treat those numbers which you have subtracted, to treat those numbers as unsigned number, and then based on the result, take the jump. However, branch, if the numbers placed in this RD and RR are not unsigned numbers but they are signed numbers, then we cannot look at the value of the C flag to decide whether A is less than B or A is greater than or equal to B. In that case, if the A and B are signed numbers, then we need to look at the value of the flags S. So if S is equal to 0, it's mean that A is greater than or equal to B, and if S is equal to 1, it's mean A is less than B, right? Now you can ask the question why mean for unsigned numbers we are looking at C is equal to 0 for C flag, and while for why for unsigned numbers we are looking at the sign flag. The first part of the question, I think it should be clear to you because I just explained on one note, right? However, the second part of the question, we are postponing it for another lecture. Okay, so like don't get stuck there. Just ignore, like keep that question in your mind, but don't allow that question to waste your time. We will answer it in an upcoming lecture later. Any questions? Okay, so there are two other instructions. A branch, if overflow flag is cleared, and branch is if overflow flag is set. So we will also talk about these branch instructions when we will be in a later chapter because they are used in context of comparing the signed numbers. Okay, thank you. So let's continue then. Okay, so how we use these branch instructions? So we use these branch instructions when we want to write the you. I think all of you know at least have some idea of if-else constructs and loops in the higher level languages, right? So, for example, if you have a if-else construct in higher level language, now how can we write it in the assembly language, right? So for that purpose, we use the branch instructions. Similarly, when we are going to do the loops, again, remember in loops, for example, if you write a for loop or you write a, let's say, do while loop, what you are doing basically there in high level languages, you are testing a condition. If the condition is true, you keep looping. If the condition is false, you terminate the loop, right? So again, when we write those high level like looping constructs and the loop constructs in the assembly language, we use the branch instructions. And jump is always when we are talking about these branch instructions, conditional branch instructions. So jump will be always in the range -64 to 63 because we have 7-bit signed number. And this is the format of the branch instructions. Like you have uppermost six most significant bits, they are contain opcode. Three least significant bits, they are also part of the opcode. And in middle, 7-bit, they are used to hold the offset K, right? Like forward or backward. So here is the example. So if you like, if you have branch same or higher instruction, so these bits they constitute the opcode, and the middle 7 bits they will hold the offset. Now let's start. Let's have a look at like more concrete example where we can use these branch instructions. So let's say we have two numbers B and A and B, and we are subtracting B from A, right? So when we subtract B from A, we both Z flag and the carry flag both will be impacted, right? Just like I have shown you earlier on one note, right? So uh, we can use the Z flag to branch when A and B are equal. It's like when we want to say that branch if A and B are equal, so what will happen? We can use the branch equal instruction, which will actually take the jump if Z is equal to 1, right? Or we can say, okay, branch when A and B are not equal. So if they are not equal, so we will use branch not equal instruction, which will under the hood checking the value of the Z flag for a value of 0. So if it's equal to 0, then the branch will be taken, right? Other option is that we can say, okay, take a jump or do the branch when A is lower than B, right? So if A is lower than B, then we can use branch low instruction or branch if carry is set. Why? Let's forget about this carry set for now. So we can use branch low instruction. And if you remember from the previous example, if A is less than B, then C is equal to 1. C will be set equal to 1. So which is saying the same thing, that do the branch if carry is set. So that's why we have another instruction which says branch if carry is set. So these two instructions basically do the same thing. Two different ways of saying the same thing. And A is greater than equal to B. So for that, if we want to say that, okay, do the branch if A is equal to B, so we can use branch same or higher instruction, which actually tests the value of C flag for 0. If it is equal to 0, it's mean A is greater than or equal to B, and then the jump is taken. And for doing the same thing, we can also use the instruction branch if carry flag is cleared, right? So because if A is greater than or equal to B's, value of C is equal to 0. So we are basically saying the same thing. Branch if carry flag is cleared. Cleared. Is it clear to everyone? Is there anything which is confusing? Okay, let's have a look at an example. Write a program that tests if R20 is same as R21. The value of these two registers are same. It tests, and if they are same, then it increases the value of R22. Increases by 1 the value of R22. So what we want to do is basically this. We need to test this condition, right? So if R20 is same as R21, then we increment the value of R22. But if they are not same, then we don't increment and we continue to the next instruction after like increment R22. So we don't want to execute an increment R22 instruction, right? Let's see how we can do this in assembly. Okay, so first thing is before I show you assembly, so I think everyone is clear on this control flow diagram. If anyone has a confusion, let me know. If you don't understand what we are doing in this control flow diagram, let me know. Okay. So now when you will be converting this control flow diagram into the assembly language program, what you will do is that here you need to first find the reverse of or the opposite of this instruction, this requirement or this condition. What is the opposite of this condition? The opposite is if R20 is okay. Let me go to OneNote because then it's clear, better for me to, faster for me to write there. Okay. Okay. So the first thing what you will do is this, that you will replace, to make your life easier. I'm just explaining this. I mean, with the passage of time, you will become familiar. You don't need to draw. You will not need to draw the figures, but I'm just explaining it here now. So you need to redraw this uh, diagram. So where you say if R20 is not equal to R21. So what should we do if R20 is not equal to R21, right? So if it is not equal to, yes, it's not. If it is not, Then what should we do? Go to the next instruction, right? Go to the next instruction. And if this condition is not true, which means their R20 is equal to R21, if this condition is not true, then increment R22 and then go to the next instruction, right? So what did I do here basically? I did nothing, but I just used a condition here. Here I just use a condition which is opposite of the original given or original condition given in the problem. So what was the original condition we were testing? If R20 is equal to R21. I said I want to rewrite the same thing by saying test the condition if R20 is not equal to R21. So if it is not equal to R21, then go to the next, which is actually follow this path, right? But if it is equal to R20 is equal to R21, follow this path, which is actually this path, right? So I just flipped the path, right? Whatever here, this was yes. So this yes part is like path is now on the no branch. The same thing what I'm doing on the no branch in this second figure, right? Is everyone clear on this? Okay. Okay. So this is like kind of critical because then it will help you to write your assembly program. Otherwise, if you directly start with this given figure, this one, and try to write the assembly program directly, it will be like more difficult for you to reason about. But if you replace it with an equivalent figure where you are simply flipping the condition, then you can more easily write the assembly program, right? Now, how can I write the program, right? So now let me take you, or can I take the screenshot and carry this figure to my slides? Yeah. Let me just reduce its size and put it here. Okay. Okay. So now let's try to write an assembly program for this one, right? So now we will say, okay, we are first giving writing the condition compare the value of R21 and R22, right? So basically what will happen, that value of R21 will be subtracted from R20, and based on that, the value of Z and C flag will be set, right? So now we can follow this one. If they are not, we are writing actually code for this figure. So if they are not equal, go to next. Branch not equal, go to next, right? And if they will be not equal, we will directly go to this point, right? But if they are equal, so this branch will not be taken, and the next instruction in sequence will be executed, which is increment R22 and then go to the next instruction, which is indicated by this next label. Don't get confused by this arrow here. Okay. Is everyone clear on this? Again, so here we are saying compare R20 and R21, which will subtract the value of R21 from R20. And based on that, the value of Z and C flag will be set. And if they are not equal, right? So now we look at this condition. So we are saying if they are not equal, go to the next. So we are writing same thing. Branch not equal, go to the next, right? But if they are equal, then don't go to the next and execute the next instruction in the sequence. Okay. So the next instruction sequence is increment R22, and then we will go to the instruction following increment R22. Okay. Uh, Now, let me know if you have any question before I say what I'm going to say in the next slide, or actually on the same slide, but something about this figure. Okay, if no questions, then if you if you notice, there is kind of one-to-one mapping. So branch next, branch if not equal next, it is same as written in this condition. And but there is no one-to-one mapping between this code and this figure, although this code is also implementing the same figure. Actually, these two figures are doing the same thing. They are doing the same operation. However, conceptually, it is easier to do or map your code to this second figure, redrawn figure, as compared to the original figure. Okay, that was like main reason behind rewriting or redrawing the figure using the reverse of the given condition. Okay, now here is another example. And this time we are testing for A is less than B, right? So write a program that tests if R26 is less than R24 and then increases R22. Okay. Again, you need to do the same thing. Actually, let's do it as an exercise. Okay. I am giving you, you can have 2 minutes. I know it will take a little bit time. So you need to write a program which implements this uh, program, a control flow diagram, right? But remember, what did I say? You can, to make your life easier, redraw it by writing the reverse of this condition. Okay, and then after that, write the program in assembly. Go ahead. I'm also doing on my notebook so that we are on the same page. Okay. Done, done, done. Okay. Okay, okay. Let's have a look then at the example, at the solution. Okay, so is there anyone who use the branch same higher to write the program? Branch same or higher instruction. You did. Okay. Same or higher. Yeah, that is like kind of more intuitive, right? uh, to use instead of saying if branch if carry is cleared, right? Both instructions are essentially doing the same thing. When you say branch same or higher, that instruction will test if value of c is equal to 0. If it's equal to 0, then take the branch. But if you say branch if carry is cleared, it will also do the same thing, but it is not more closer to human intuition as compared to branch same or higher, right? So I actually did exactly the same thing, but instead of here saying branch CCC, I said branch same or higher L1. Otherwise, everything is same. Anyone who didn't understand this example and who want me to do it on one note, even if there is a single student, I will do that. Uh, According to this example, since is this example they said L1, so L1 is basically a label. Label can be anything, but only requirement is that it is followed by a colon, right? So you can write your name. For example, I can say instead of L1, I can say Naveed and then colon. It can be anything. Okay. Is there any one student who want me to do it on OneNote? If yes, let me know. Otherwise, I will go to the next slide. Even if there is a single student, I will explain because this is important. Okay. So let me first simply copy this figure from here to OneNote, right? And ignore these like this one and two. That's just like bad cropping of the figure. Okay. So now what we need to do is, so first thing you need to do is you need to redraw this one by using the opposite or reverse condition, right? So I am saying if R26 is greater than or equal to R24, right? And I am putting it in a diamond, right? Okay, so if R26 is greater than equal to R24, then what should I do? I need to follow this path, right? So this is in this redrawn figure, it is yes path when the condition is true, right? So simply go to L1, label L1. And if R26 is not greater than or equal to R24, then do what? No, which is yes path in the original figure. So what I need to do here then, I simply say increment R22, right? And then go to the L1, right? Now, how can I write the code? So I simply compare R26 with R24. And now what I'm saying, if R26 is greater than or same or higher than R24. So branch if same or higher. Branch if R26 is same or higher as R24, where to L1 here, right? And L1 is something here, right? And if it is not, then what will happen? Go to the next instruction in sequence. Don't take jump to this label, but do the instruction next in sequence. So what it should be? It should be this one, increment R21. Increment R22. Okay. So now if R26 is same or higher than R24, this instruction will not be executed. Control. So after this instruction, then so first this instruction will be executed. Second one will be this. So if R26 is greater than R20, the third instruction that will be executed is one which is pointed by this label L1. But if R26 is not greater than not same or higher than 24, then what will happen? So first this one, second one, and this will be the third one. Okay, clear? Please confirm if it is clear to you now or not. If not, I can try again. Okay. Okay. Thank you. Thank you. So, okay, now let's go to the next example, right? Uh, so again, branch CC and branch same or higher are two different names for the same instruction. How? I already explained because both check the C flag. Okay. Now, write a program that tests if R26 is greater than R24 and then increases the R22. Actually, this is like, okay, let's do it this time now. No, okay, give it a try. Everyone, you have 1 minute or maybe 2 minutes, 2 minutes. So let me know if you are done. Thank you. Okay. By the way, let me say this before I forget. I have released the instructor evaluation form, or actually it is a quiz, but ungraded quiz. It says graded, but it has 0 points. Okay. So please make sure that you uh, participate in that evaluation quiz. Okay. So actually it is same, like you are comparing, and then you can say branch if low, right? Or you can use branch if carry is set. Why? Because when you say branch if low, so you ask basically it checks the value of the carry flag. If the value of the carry flag is set equal to 1, it's mean that R26 is less than R24, right? And you will get this program. Anyone who wants me to explain it on OneNote? Okay, before I go to OneNote if needed, before that, let me tell you what is meant here by k is equal to 1 in BRCS. So actually, I didn't also explain it in the previous slide. Let me explain for this slide and then we'll go to previous one. So here, what is PC? So when you are branching, when you are executing branch instruction, so PC is pointing to this instruction itself. What is PC plus 1? PC plus 1 is the next instruction in sequence, which is increment, right? And the instruction which will be at L1, it will be what? Well, the one which is after the increment, right? So if the branch is taken, let's say that R26 is uh, smaller than R24, right? So then what will happen? That you are saying that, okay, go to the L1, right? So what will be the value of K, right? Like, remember, if the branch is taken, the value of PC is set equal to PC plus 1 plus K, right? So if this is PC and this is PC plus 1, so the next one in sequence will be PC plus 2, right? So it's mean that the value of K needs to be 1, right? Clear? Same thing here. So this is PC plus 1, and the instruction at in sequence after the increment instruction will be PC, its address will be PC plus 2, right? So if this branch is taken, the PC will be set, the new value of the PC will be set equal to PC plus 1 plus K. What should be the value of K so that it becomes equal to 2? The whole address becomes, it should be equal to 1, right? So it becomes PC plus 2, so that it points to the instruction pointed by the label 1. Okay, as I said, branch, if carry is set or branch low, they are the two different names of the same instructions, or two different ways of saying the same thing. Any questions? Okay, let me check the time. We have a couple of minutes. So, okay, now let's do this example, if and else. Previously, we were doing only if, right? We were not doing the else part. Now we are going to do the else part as well. Okay. So, and here we are treating R20 and R21 as unsigned number. So what is the program? So we are basically want to do that, put 5 in R17, right? And then if R20 is greater than R21, then increment R22. If not, then decrement R22. And then this instruction is independent of if else, so it will be always executed, which is increment R17, right? So go ahead and give it a try. And again, as I said, the best way is to redraw the figure and then then write the code. So I'm also doing the same thing here. Okay, the one thing is that you can have this, condition if R20 is greater than R21 is same as saying if R21 is less than R20, right? Okay. Okay. Let's wait some more people to complete. Okay. Okay, so let me first show you how I did it, because there can be different ways of doing it, but I think the way I did is a bit different. So different from slides, I guess. Let me just take it to the OneNote. Right. So So if I write the condition, if I read this condition as R21 is less than R20, it is same as saying R20 is greater than if R20 is greater than R21, it's mean R21 is less than R20, right? So I'm reading it as if R21 is less than R20, right? So I am rewriting R17 is equal to 5, and then I am writing reverse of this condition, which is if R21 is greater than or equal to R20, right? So I'm just putting it in a diamond, a weird diamond. Okay, and if it is greater, then this is yes path, which is basically no path in the original one. So I'm saying decrement R22, and in no path, which is yes path in the original figure, I'm saying increment R22, right? And then here I am saying increment R17, right? So how can now I write the code? Load immediate R17, 5, then compare R21 with R20, and branch if same or higher, right? This then take the yes path, which is decrement. So here I'm saying decrement, and here I can write dec R22. But if this condition is not true, then I need to follow this path. So here I can say increment R22. Now, one thing is that which I think we have not covered in lecture is I need to use jump instruction. Why? Because after incrementing R22, I don't want to do decrement. I need to go to this increment instruction, right? So I can say here increment, let's say let's not say increment to confuse. Let's say end, right? And here I can put end, and it will be increment R17. Now let me just explain. So if R21 is same or higher as R20, so what will happen? I will jump to the control will go to the decrement label, which is this one, right? So R22 will be decremented here, and then the next instruction that will be executed will be the one in sequence, which is increment R17, this one here. But if R21 is not same or higher as R20, right? Which means R21 is less than R21 is less than R20, then what will happen? That branch will not be taken to the decrement label, and next instruction in the sequence which will be executed, which is increment R22, and then I will take jump to the end. So here, increment R17. Okay. So is everyone clear on what I explained? So let's first look at the solution two, because solution two is what I showed you on OneNote, right? So here you are doing exactly the same thing. Compare R21, R20. If same or higher, then increment R22 and then jump. I mean, this is like kind of a weird way or different way of saying the same thing. So yeah, we have a quiz. Yes, let me check the time. Ah, yeah, go ahead. Go ahead and we can start from the same slide in the next lecture. So it's time for you to do the quiz. Okay. I'm stopping it here, but I am online until end of the quiz time, lecture time.